So hi everyone. So I will present a work about Langevin Monte Carlo algorithm after two US works, two US talks. We will have two French talks now. So the main goal here will be to draw some further similarities between sampling algorithms and algorithms on optimization. And in order to present these similarities, let me start with the very basics of these two problems. So in the optimization theory, we are interested in finding a theta star which minimizes the function f of theta. So the function f here is exactly the same as in the first talk of this session. And in the problem of sampling, we want to draw randomly theta according to the probability density function pi of theta, which is proportional to the exponential of minus f. So the most used methods in these two problems are the following. In optimizing the function f, we are always using, or we are very often using the gradient descent defined by this formula here. So h here is the learning rate, and so we have the gradient of f in the formula. And when we are trying to draw a random point from the probability density function pi theta, we use something which is very similar to this gradient descent, but with an additional random noise, which has a variance proportional to square root of h, and all these psi k's are IID Gaussian random vectors with identity covariance matrix. So now, so we see that the problems are similar, the methods are similar, and let us have a look on the theoretical guarantees for these two methods. So for looking at the theoretical guarantees, it's more convenient to consider the simplest case of convex optimization. So we will assume that the function f here is small m strongly convex. So the first formula here means exactly the fact that f is m strongly convex. And the second line tells us that f is smooth, which literally means that the gradient of f is Lipschitz with constant capital M. So the very well-known theorem of the optimization theory tells us that if this learning rate h is smaller than 2 over the Lipschitz constant, then we have this exponential convergence of theta k to the optimal value, where this constant rho is given by the explicit formula written in the theorem. Now let us look at the corresponding theorem for sampling from the density pi. So the W2 in this formula is the Wasserstein 2 distance introduced by Max in the previous talk. And here this, sorry. So here, this nu k is just the probability density function of the Langevin Monte Carlo algorithm kth iteration. So what we see here is that this Wasserstein distance between the kth iteration and the target density decreases when k tends to infinity and when the learning rate h goes to 0. And in the first term, we have this exponential decay. In the second term, we have a linear decay in h. And if we look at the differences between these two theorems, there are at least 3 of them. The first difference is that for h, we have a condition which is stronger than the corresponding condition in the optimization theory. The second difference is on the definition of this parameter rho. So it's not the same, and the rho here is larger than the rho in the optimization theory. And so the third difference is that actually the theorem in the optimization theory is much more elegant than the theorem in the sampling, because there is this remainder term which is kind of messy. So our goal was, my first goal was to clarify why we have these differences between these two theorems, whether we can do better, and if we can do better, whether it can be extended to the stochastic case. So the first result is that we can do better using exactly the same theorem, but being more careful. We don't modify any argument in the proof, but just change a little bit the combinations of the arguments, and we get a result which is the exact analog of the result in the optimization theory. So the condition on h here is exactly the same as in the optimization, the rho, parameter rho is the same as well, and the remainder term can be written now in a very simple form. And then, when we have this very simple theorem, we can try to extend it to the case where we are not able to evaluate the gradient exactly, but we have access to some noisy versions of the gradient. So let us assume now that for any point theta k, we are able to compute the gradient plus some noise. So for the noise, we will only assume that the expectation is equal to 0, and the expectation of squared norm is upper bounded by p. So so in this case, we still can use this Langevin algorithm. The only modification is that we replace the gradient by its noisy version yk. And if we try to state a theorem similar to the previous one in this noisy setting, then the corresponding result tells that if we take, so this is the simplest version of the theorem. In the paper, the theorem contains also another case where h can be up to 2 over capital M. But at least when h is smaller than this value here, then we have an upper bound on the Wasserstein distance, which is very much similar to the previous one. The only additional term here is this sigma squared multiplied by some constant, where sigma, recall, is the standard deviation of the noise when we observe the noisy gradient. So basically, the main message of this theorem is that if you have a noise in the gradient with a bounded standard deviation, then you have very strong inequalities on the Wasserstein distance, which are basically the same as in the non-noisy case. Yeah, thank you.
Question, why did the next speaker set up? Will you separate between sigma and p in the last how it works?
Yeah, so actually your vector zeta here, the noise, is p-dimensional. So it's interesting for us to see the dependence on the dimension. So it's natural to separate between sigma and p here.